The last colligative property that we're going to take a look at and actually quantify is called osmosis or osmotic pressure. Well, the process of osmosis you've probably heard about in another class. Semi-permeable membranes, especially those in cells, can allow some particles to pass through but block other particles. And in biological systems, most of those semi-permeable membranes in a cell membrane allow water to pass through, but maybe not some solutes. So if you look at this diagram here, you can see that in osmosis, there's a net movement of solvent from the area of higher solvent concentration to lower solvent concentration. Now for me, that doesn't make sense. I'm going to kick this into practical way of looking at it. In the first picture right here, you can see on the left there's a concentrated solution that's darker than that on the right-hand side. The one on the right is dilute, and they're being separated by a semi-permeable membrane. So if I'm going to allow water to pass through that membrane, let's use our common sense. Is the concentrated solution on the left-hand side spontaneously going to get even more concentrated? Or are the driving forces of entropy going to push some water through from the right-hand side to the left-hand side to try to dilute out the concentration on the left side of this U-tube? I think you know the answer based upon my explanation. If I can highlight those little arrows right here in the center, hopefully you can see there's a greater arrow showing there's a net driving force to push water molecules towards the left. And as you look at the center diagram, you can see on both a macroscopic and a particle view what's happening. The color of the solution on the left has gotten more dilute and lighter color, and also the level of the solution has risen on the left tube and dropped on the right tube. Kind of looks like one of those manometer tubes. If you carefully look at the pictures down on the bottom, you can see that what's happening is the semi-permeable membrane prohibits solute from passing through either direction, but allows water molecules to pass through. And there are more symbols of water molecules passing from right to left than vice versa. So hence we see the liquid rise on the left-hand side. Well, that's the process of osmosis. But if you wanted to stop the process of osmosis, osmosis is a process or a thing. Osmotic pressure is how hard would you have to push down on the left-hand side of the U-tube to exert enough pressure to stop net movement of that solvent across the semi-permeable membrane. And of course, since this is a colligative property, the greater the number of particles that are in solution, the more pressure you're going to have to apply to stop that osmosis. So the concentration, higher solvent, lower solute, that part's confusing to me on this definition at the bottom. But if I look at it from a common sense point of view, it makes sense. So now, as we look at this osmotic pressure or pi, that equation looks very similar. Actually, before it gets simplified to solve for osmotic pressure, it read pi v equals nRT, just like PV equals nRT. Rearranging the equation to solve just for osmotic pressure, you would have N over V times RT. Well, of course, you know the number of moles divided by the volume in liters is the molarity. So we can use osmotic pressure problems to solve possibly for molarity of unknown substances or to calculate the osmotic pressure itself. Let's take a look at a sample exercise. Now, before we get in there, though, I will actually be following up with a few slides talking about the concentrations of substances. And if the osmotic pressure is the same on both sides of that membrane, we call that being isotonic. Iso means same. Here's our sample exercise 13.11. Please use this for any of the questions that you have on osmotic pressure in your worksheets. The question says, the average osmotic pressure of blood, notice they're measured in atmospheres, is 7.7 at 25 degrees Celsius. what molarity, not molality, will be isotonic with blood. Okay, let's see what I know. I have a pressure. There's my P. I've got my gas constant. There's my R. The temperature is 298 in Kelvin, 273 plus 25. So I can set up that my molarity, if pi equals molarity times R times T, molarity should be equal to osmotic pressure over the gas constant times the temperature. So it's fairly easy to solve for this particular problem, 0.31 molar. So essentially what we're saying is that if you want the concentration of glucose to be the same as that in blood, you would have to give that person a 0.31 molar concentration in solution. Now, what we are going to show you is a practical application of this. And when you go to the hospital, I'm not going to do this sample exercise here, so I'm going to scoot along. Oh, I will. Take back. The osmotic pressure of a particular solution was used to determine the protein's molar mass. So we're given the molar mass in milligrams. Watch that guy. We have 5 liters of solution. They tell us the temperature and they tell us the osmotic pressure. So we're going to pretend that it's not an electrolytic substance, so there's no Van Hoff factor to worry about. And we've taken that equation again to solve for molarity is equal to pi over RT. Here is the pressure in torr, though, being turned into atmospheres by dividing by 760. Here's my gas constant, temperature in Kelvin. And we've solved for the molarity, 8.28 times 10 to the negative 5 moles per liter. Now, if I go back and reread what they gave me, they want me to find its molar mass. I'll need to find the moles. I've been given grams or milligrams, so if I can find grams per mole, I'll be able to find the molar mass. So here is my molarity, and as you know, molarity equals moles divided by liters. So if I want to solve for moles, let me say that again. Molarity is equal to moles divided by liters. If I want to solve for moles, I would take molarity times liters. So I've got my molarity, I've got my volume, changed milliliters to liters, I've got the moles. We're almost there. Sharp-eyed people would have seen that if I'm trying to get the molar mass, I have to make sure I take 3.5 milligrams, turn that into grams by dividing by 1,000, and now I have my grams, I have my moles, and simple division will give me the molar mass. So the practical application that I started to talk about a moment ago is that when a person is in the hospital and is being given an IV of electrolytes or glucose or whatever, you have to be very careful in your concentrations. So let's take a look at this example. This is where the solution is hypertonic. That doesn't mean anything to me. Let's think of it this way. If the concentration outside a cell is high, then the cell membrane says, hey, let's squirt some water out through our semi-permeable membrane to try to dilute out that high concentration of the solute outside the cell. Well, consequently, the water flows out of the cell and you get the shrinking of the cell called crenation, which can impact its function. If the solution is not hypertonic, which means too concentrated, but if it is hypotonic, which means not concentrated enough, then the water outside goes, okay, wait a minute. The concentration outside is low compared to inside. We want to shoot some water back inside the cell to try to equilibrate the concentration on the interior with the concentration in the interstitial space. So if water flows into the cell, the cell swells up and you can get what we call hemolysis, blood, lysis, bursting. So you're going to burst the blood cells. So getting the exact correct concentration necessary for human biofunctions is important when you're getting an IV. That, I believe, is the last topic on colligative properties. We will not be doing any kinds of vodcasts or lecture or problem sets on colloids. Please use these 3 or 4 mini vodcasts I've recorded to help you solve any of the problems that you have on the worksheets for colligative properties for Chapter 13.